All right, so this section is called the side splitter theorem, and it does exactly what it sounds like. It splits the sides of a triangle and splits them proportionally. So looking at this theorem from the ground up, we'll kind of build it up and show you why it works. So we have a diagram of triangle ADE, which is the outer triangle here, and segment BC has been drawn parallel to DE. So we want to justify why these triangles are similar. It goes with the triangles we've been working with lately, where if you have parallel lines, you have corresponding angles, and those corresponding angles will lead to an angle-angle similarity proof. So we know they're similar. Now that we know they're similar, we can start working with their segments. So we know that AE, which is this outer segment on the right, is corresponding to AC, and AD is corresponding to AB. So that proportion there is just showing what we know about similar triangles. If we have these particular numbers now, we can insert them into that proportion. So if AC equals 9 and AD equals 10 and AB equals 6, this proportion from the diagram becomes the numerical version, and we can solve for AE. We can also solve for CE, because if AE equals 15 and AC was 9, then you can just subtract to get the remaining portion. So that CE would have to be 6 there. So to find the following ratios of lengths that there are similar simplest forms and compare. So we're looking for AB over BD. So AB was 6 and AD was 10. That leaves 4 for BD. So we're saying 6 over 4. And AC was 9 and CE was 6. So if we compare those, we get 9 over 6, which is 3/2. And so those ratios are the same. So what we're saying then is the parallel line segment split the sides proportionally. And that's what the side splitter theorem says. The side splitter theorem says that if two lines are parallel, or if we have a segment parallel to the third side of a triangle, then that parallel line will intersect the other two sides and divide them proportionally. So the two partial segments on the left will have the same ratio as the two partial segments on the right. All right, so given that this diagram algebraically proved the side splitter theorem. Now you have to pay attention to this. It's a little bit tricky. So if we have similar triangles because of those parallels, which we've already shown at the top of the page, we have the proportion that we said. It's going to be AE over AC equals AD over AB. What we can do here is split AE into its two segments, AC plus CE. All right, so this numerator here on line 2 is simply taking AE and splitting it into its two parts. Didn't do anything else with it. And the same thing happened with AD on the right side. It becomes AB plus BD. Okay, now from there, if we do a cross product and we take AB times this binomial, we get AB times AC, and we get AB times CE. So I'm essentially distributing AB to its cross product. Doing the same thing on the other side, distributing AC to AB and BD. And so I have AB times AC and BD times AC. Notice here that we have the same quantity on both sides. We have an AB plus times AC over here. We have another one over here. So those will subtract each other out, and that leaves us with AB times CE equals BD times AC. So if we have that, then we can divide both sides by both BD and CE, and that leaves us with the proportion that we're trying to get. Okay, so that's why it works. That is the last time you're going to have to understand why it works. But just know that it wasn't just dreamed up, and it wasn't that it only worked in that one specific example at the top of the page. It will always work because of this proof. But what you need to know is that if the lines are parallel, the splits will be proportional. That's it. Okay, on the next page, the side splitter theorem helps us to solve parallel line triangles because we don't need to know all the information about the triangles. We only need to know partial information. But we do have to know the lines are parallel, so that's the first thing, and it states that for us here. Once we have that, then our side splitter theorem is going to work. So what you see here is a segment TZ and a segment WZ. That's going to be important because those two are completed, right? Those two corresponding parts of the triangles are given to us with numerical form. So looking at trying to find segment ST. ST is in the middle. It's going to go with VW in the same way that TZ goes with WZ. Okay, so if I write a proportion with ST over TZ, that's this side of the triangle, and VW over WZ is this side of the triangle. My proportion can say X or ST over 25 equals 6 over 15. And it just makes it very simple to solve. We end up with ST equals 10. Okay, now UV and VW are here, and RS and ST are here. So now that we know that ST is 10, I can say 15 over 10 is the same as UV over 6. All right, all of those consecutive segments are going to work in proportion, and it solves for UV equals 9. So that's how side splitter works. You just set up proportions along the side of the big triangle and set them equal to the fractions from the other side. You just have to make sure that the sides are parallel, that these lines intersecting are parallel, otherwise it doesn't apply. All right, exercise 4, a right triangle has one of its legs divided into segments 2, 3, and 5. Lines parallel to the other leg are drawn, and it's dividing into 3 segments as well. It's telling us that the whole length from A to D is 30. Now we don't know what each individual segment here along AD is equal to. However, we do know that it's got to be some multiple of 2, 3, and 5, because everything's supposed to be proportional coming across this side splitter. So if I labeled AB with a 2x and BC with a 3x and CD with a 5x, I'm saying that there's the same scale factor that applies to all 3 to get from the left side to the right side. So that's where the equation is coming from here in this box. 2x plus 3x plus 5x equals 30, so x comes out to 3. Once we know that that's giving us the multiplier, the scale factor, so if everything's been scaled by 3, 2 becomes 6, 3 becomes 9, 5 becomes 15. All right, so side splitter will work even if we don't have a completed segment, because we know that the ratios are going to apply. All right, it should be noted the converse is also true. So if we know the sides are proportional, that's a way to prove that the lines are parallel too. We don't always have to go from parallel to proportional. We can go the other way. All right, so in this diagram, we know that AB is 10, BC is 8. Those are both labeled. And that AD is 15 and DE is 12. So we have all of that. If I want to prove, well, actually, it's not telling me what to prove just yet. So it's asking me first to verify that the proportions hold true. So is AB over BC the same as AD over DE? And that is. So it would be another way. So we talked about how you can test for proportionality using a cross product. Both of these diagonals equal 120. They also both reduce to 5/4, so there's a couple ways you can prove it, but they certainly are in proportion with each other. If you look at AC and AB, that's going the total over the part, so it's 18 over 10, and also 27 over 15. Those cross products would both be 270, and they both reduce to 9/5. So both of those proportions are true. So based off of that, what is the dilation factor? Now you have to be careful with this. Side splitter works for solving for unknown segments. It does not work for establishing a scale factor, because AB and BC are not corresponding within triangles. You have to look at the AC segment and compare it to AB in order to get the scale factor. Okay, so BC is part of a trapezoid. It's actually not part of the triangle at all, so you cannot use that to get a scale factor. So if I'm trying to get a scale factor, I want to take this full segment 18, divide it by this partial segment 10, reduce it to 9/5. That's my scale factor. Okay, so how does knowing that those triangles are similar show the lines are parallel? Well, if two triangles are similar, those corresponding angles will be equal, angles 1 and 2. And if those are congruent, then the lines that form them have to be parallel as well. So all of this concept, side splitter, similarity, it all kind of goes together. The one thing I want to make sure everybody heard is that if you are doing side splitter, that does not give you a scale factor. It only gives you a way to solve for missing segments. If you need a scale factor, you must use the entire triangle segment when you're trying to calculate it.